Hello folks, and welcome to this lesson on entropy. By the end of this lesson, you should be able to predict whether a physical or chemical change will result in an increase or decrease of entropy in a system, and calculate entropy changes using standard entropy values. Now, the idea of entropy is an interesting one, and in the common sense, it is referred to as a measure of disorder. A quick example that might give you an idea of what I mean by a measure of disorder is if you take something like gases. Gases have all of these particles that keep on moving all over the place. Whereas if you take a solid, you have all of these molecules that move very little. All they really do is vibrate in space. And so something like that solid is going to have a low amount of disorder. Things are pretty orderly, whereas your gas has a lot of disorder. Now, to give a slightly different definition of entropy, we have the measure of distribution of matter and or energy in a system. So again, if we're going to take that solid versus gas as an example, if you take a gas, there is matter that is distributed in far more of an area, and also the energy is going to be distributed quite a bit as well, as opposed to a solid where everything is not going anywhere. There isn't much distribution. Now, if you have more ways to distribute energy, then your entropy is increased. So that gas has high entropy, whereas your solid has low entropy. There are units for entropy, and it is joules per Kelvin per mole. And there are a few things that you need to be aware of when you're dealing with entropy. First thing is, do note that the unit is not kilojoules, it is joules. And so when you are doing calculations where you're also dealing with enthalpy or Gibbs free energy, which we are going to get to, you are going to have to make sure you do unit conversions so that your calculations work out. So be aware of that, the fact that you have joules. The second thing that you're probably going to notice is that kelvins are involved. So this should indicate to you that entropy is a very temperature dependent thing. Temperature can impact entropy quite a bit. This is in contrast with enthalpy, where even if you change the temperature that the reaction is working in, it's probably not going to change much in terms of the overall change in energy or heat of that entire system. Entropy is going to depend quite a bit more on what temperature you're working at. Now, one thing that you might be asked to do is take a look at a reaction and predict, not based on numbers, but based on what you are seeing happening in that reaction. Is the entropy of this system going to increase when this reaction happens, or is the entropy going to decrease? So for this, remember that you are going to look for numbers of ways to distribute energy, because an increase in number of ways to distribute energy is going to increase entropy. So knowing this, you are going to compare your reactants and your products, and you're going to be looking for a few things in terms of that whole number of ways to distribute energy. One of the big ones is going to be states. So take a look and compare your reactants versus your products. Does one side have more solids than the other? Does one side have more gases or liquids and solutions? In general, your solids have the least amount of entropy and your gases have the most amount of entropy. So if you're starting with the solid on one side and then you are going to end up with a gas on the other side, it's probably going to be likely that you are increasing entropy in this reaction. Now, something for you to keep in mind in terms of solutions is remember that if you have a highly soluble ionic compound in solution, it is going to dissociate into its ions, and keep an eye on the number of those as well. Because if all things are equal, in that it's all solids on one side and all solids on the other side, or all gases on one side and all gases on the other side, you want to take a look at how many moles of everything there are. So if you have all gases everywhere, then what you want to do is look and see if there's a difference in how many moles worth of gases there are on either side. If one particular side has more moles of gas, then depending on which direction you're looking at, that side is going to be more entropic. So if we're going to go through a few examples, if you're taking solid sodium hydroxide and you're dissolving it in water, going from that solid to aqueous state is going to be an increase in your entropy. You have more disorder because now your ions are going to be floating about in that solution. For this next example, you will see that you have all gases on both sides, but you do have a total of 4 moles worth of gas on the left side as opposed to 2 moles of gas on the right side. So you have more ways to distribute that energy with the 4 moles of gas on the left versus your 2 on the right. And so this second equation, you're actually going to be decreasing that entropy. Now for this third example, everything is in solution. So let's take a look at species to introduce that disorder. You have your sodium hydroxide, which is going to give you sodium ions and hydroxide ions, your hydrochloric acid, which will give you hydrogen ions and chlorine ions, as opposed to your right side where you have water, and then you will have 2 moles worth of ions. So you have 4 moles worth of ions on the left side and really 3 moles of liquid solution-y stuff on the right side. And so this third one is also going to be a decrease in entropy. Now, something that I want to note is that when it comes to entropy, an increase in entropy is generally favorable, energetically favorable. Now it's a little bit different than enthalpy, where a negative enthalpy, so an exothermic reaction, is energetically more favorable. So a decrease in energy in your system is more favorable. In terms of entropy, an increase is going to be more favorable. Now I'm not going to talk about it too much more, but in terms of the universe as a whole, entropy of the universe as a whole is always increasing. So the tendency for the universe and everything is going to be towards an increase in disorder, an increase in entropy. And since the universe has that sort of tendency, you can also see that sort of favorability in terms of reactions as well. Now, hopefully unsurprisingly, there are quantitative ways of calculating the entropy of reactions as well. So unlike your enthalpy values where you cannot find the enthalpy of a specific compound, you can actually find the absolute entropy of a specific substance. So any of the values that you see in data tables where they tell you what the entropy is, you're not dealing with a reaction starting from where the elements are and all of that in standard state. It's none of that. Every substance has its own entropy. And so yes, you can find these standard entropy values, and something that you might notice is that elements do not have an entropy of 0 necessarily. Think about it. If you have something like oxygen gas, oxygen is a gas in standard conditions. So if you're going to look at oxygen in standard conditions, there's going to be a lot of disorder in there. There's a bunch of entropy in there. And so that value is not going to be 0. As a reminder, the units are going to be joules per mole per Kelvin. Remember that it's joules and not kilojoules. And probably also unsurprisingly, if you want to find the change in entropy of a reaction, you're going to take the entropy values of all of your products, subtract it by all of your reactants. Remember, stoichiometry is going to take place in here as well. So if we're going to take this particular reaction as an example, then when you calculate, you're going to take all of the entropy values of your products. So you have 2 moles worth of that NH3, and then you're going to subtract it by the entropy of all of your reactants. So there's the entropy for N2, and here is the entropy for H2, and you have 3 moles worth in this balanced chemical equation. So you're going to get a negative value there, and this should not be surprising because we did mention in the last slide that this is going to be a case where your entropy is decreasing. And so yeah, you get a negative value there. So that's the end of this lesson. I'll see you next time.